Hey guys, this video is going to be on Lewis structure exceptions, resonance structures, and formal chargers. So let's start off with Lewis structure exceptions. Our initial focus is going to be on octets that are incomplete. Okay, there are other exceptions that exist, such as radicals. We're going to limit ourselves to centralized atoms that don't quite hit 8. So in some compounds, the number of electrons surrounding the central atom in a stable molecule is actually less than 8, right? Incomplete octet. One of the kind of more popular examples is that of beryllium. Very often beryllium only needs a total of 4 shared electrons to be considered stable as it engages in bonding to form a molecule. So as just a quick example, we here have beryllium hydride, where we find that beryllium between the 2 shared or bonding pairs only has 4 total electrons. Another kind of classic example is that of boron, and also aluminum, as it's found within the same group or column. Boron tends to form compounds where, again, we're finding that we have less than 8 electrons and that the octet rule is incomplete. Or I'm sorry, the octet is incomplete. The octet rule has not been followed. So both here with the boron trifluoride and the aluminum chloride here, we see that in both cases, the boron and the aluminum only have 6 shared pair of electrons, but both these molecules are actually quite stable. Okay. Again, there are other exceptions that exist. Beryllium and boron will be some of the more popular ones that we encounter. Okay. And today in class, we actually saw that sometimes when we draw Lewis structures to represent a molecule, we find that there might be several possibilities, and it can be tough to decipher what is the correct Lewis structure. Whenever we find that there are more than 2, when there's 2 or more, valid Lewis structures, we refer to these things as resonance structures. Okay, they're shown with double-headed arrows, and we'll see that here in a second, between them to indicate that the actual structure is on average, or it represents an average of these 2 resonance structures, or 3 or 4 or however many exist. So no individual picture is itself indicative of what's going on. You have to kind of take a look at the full picture, all the resonance structures, in order to decipher the true nature of a molecule. So let's kick things off with sulfur dioxide. Okay, I've skipped a couple steps here, and what I've written are actually the resonance structures. So we would progress through kind of the normal steps as far as coming up with a Lewis structure. We find that that double bond in between the centralized sulfur and that peripheral oxygen can exist either in this location or in between the sulfur and the other oxygen. Okay. Now again, this picture does not represent sulfur dioxide, nor does this one. It is both of these pictures taken together that offers kind of true insight into this molecule. Through experimental evidence, we're able to determine that we don't have bond lengths of different sizes, right? We don't really have a single bond or a double bond, but because these electrons are kind of migrating, kind of back and forth, we have kind of this single state where the true nature of that sulfur-oxygen bond is kind of at about 50% single bond character and 50% double bond character. So what I've attempted to illustrate here is that it's not just a single bond, but there's a little bit more going on here, okay? Before we get to a second example, let's just take a look at this idea of bond order. When we talk about bond order, we talk about the number of bonding pairs of electrons between 2 atoms, okay? And it's pretty simple to digest. When we talk about covalent bonds between 2 atoms, whenever we have a single bond, we're talking about a bond order of 1. Whenever we have a double bond, we have a bond order of 2. Whenever we have a triple bond, we have a bond order of 3, so on and so forth, okay? Bottom line is, the higher a bond order is, that means we're going to have a smaller bond length, so we might expect a triple bond to be shorter than a double bond, which would be shorter than a single bond. And the implication here is that those bonds tend to be stronger, okay? Now, in molecules that have resonance, the bond order does not necessarily need to be an integer, okay? It doesn't need to be 1 or 2 or 3, but as we saw in that sulfur dioxide example, we're kind of in between a single and a double bond. Okay, so going back to that sulfur dioxide example, when we have two bonding groups, right? Here's a bonding group, here's a second bonding group. We find that between those two bonding groups, we actually had 3 total bonds, right? We had 1, 2, 3 total bonds. And so what we do is we take the total number of bonds, we divide by the bonding groups, and we find that on average, we're again somewhere between a single and a double bond. And so our bond order specifically is 1.5, okay? We can extend this to a second example, and this is actually the one we dealt with in class today. We took a look at NO3 or nitrate, okay? So let's take a look. So I've taken the trouble to come up with the 3 different resonance structures for the NO3 and all we're really doing is pushing around the location of that double bond, right? So whether it's between this, between the nitrogen and this oxygen, or nitrogen and this oxygen, or it's nitrogen and this oxygen, they're all kind of equivalent, right? And again, no picture taken by itself represents the nature of NO3 We have to kind of take a look at all 3 together. And so what we find experimentally is that this NO bond, again attempting to show that it's not just a single bond, has about 67% single bond character and 33% double bond character. It's kind of somewhere in between, right? It's 8 electrons kind of migrating in between 3 different bonding groups. And so in order to calculate the bond order, right, again, we see that there are 1, 2, 3, 4. There's 4 bonds that are, kind of shared between 3 different bonding groups. 4 divided by 3, we find that the bond order is about 1.33. So not like what we saw in the SO2, where it's 1.5 and about 50-50 between single and double, but we find that the true nature of this NO3 polyatomic ion, the true nature of that bond is closer to being single bonded in nature. And again, this bond order would be reflective of length and ultimately strength, okay? So for SO2 and for NO3 all these resonance structures are equivalent, okay? But this is not always the case. Sometimes there is a best Lewis structure that we can have, and to evaluate Lewis structures to figure out what represents what is likely to be the true nature, we have to consider these things called formal charges. When we talk about formal charges, this is the electrical charge difference between the valence electrons in an isolated atom, okay, so just looking at the atom by itself, and then the number of electrons assigned to that atom once it's engaged in chemical bonding, and we've actually drawn it in a Lewis structure. This definition will become a little bit clearer as we look to work our first example, okay? So before we get to that first example, let's talk about some considerations, okay? When we talk about formal charges for molecules, which we are actually about to take a look at a ion, okay? But for molecules, given that molecules themselves are neutral, the sum of the formal charges must also be neutral and must cancel out towards a net neutrality. But for ions, whenever we start drawing in formal charges, they will equal the charge of that specific anion or cation. Okay, so the sum of the formal charges must yield the overall charge, whether positive or negative, of the ion itself. So how do we determine this? Right? What are the rules for determining formal charges? And again, we'll see these in action here in a second. The first thing we want to do is count all the atom's lone pair of electrons. Okay, and then we're also going to count half of the shared electrons. And this is what we call kind of the valence electrons that have been assigned. Okay, so we have assigned electrons to specific atoms in the context of their Lewis structure. Okay, what we will do is we will actually subtract the number of assigned electrons that we just determined, okay, via this method here, in 1, from the number of valence electrons in the free neutral atoms. All we'll do is, we'll take a look at the that outer valence shell, and either we can revert back to the electron configuration, or we can just take a look at the column that that atom resides in on the periodic table, okay? So Let's work our first example. We're going to take a look at the polyatomic ion NCO -1. And so what I've already done is I've already drawn out the 3 possible resonance structures where we have a triple bond between the carbon and nitrogen. That triple bond is migrated over between the carbon and the oxygen. And then we have kind of this resonance structure here in the middle where we actually just have 2 double bonds, okay? So the first thing I want to do is I want to go through and I want to talk about the valence electrons for each one of these elements, okay? With a quick reference to the periodic table, and I see that nitrogen is in the 5th column, carbon is in the 4th, and oxygen is in the 6th here. So carbon is going to have 4 valence electrons, nitrogen has 5, and oxygen has 6. And we can write that through as we look to evaluate all 3 of these resonance structures. Okay. The next thing I want to do is talk about electrons that are assigned. Okay. So what I'm going to do is I'm always going to cut those shared or bonding pairs kind of in half. So I'm going to take this triple bond and I'm going to just cut it right through the middle, single bond right through the middle, double, double, single, triple. Okay. And now when it comes to assigning electrons, I see that this nitrogen has 1, 2, as far as these lone pairs, and then a 3, 4, 5. Okay, so 5 electrons I can assign that nitrogen. So again, it has 2 electrons right here, contained within that single lone pair. And then there are technically 6 bonding electrons, right? 6 shared electrons, but I'll cut that number in half per the rules for determining formal charges. And that's where I'm coming up with my 5. I think by cutting that triple bond in half, what I kind of do is I look at like just a portion of those bonds and I see like, oh, there's only 3 electrons attributed to nitrogen there, being assigned to nitrogen. I'll do the same thing for carbon. 1, 2, 3, 4. For this oxygen, it has 1, 2, 3, 4, 5, 6, 7. So what I find is that the difference for nitrogen and the difference for carbon is both 0, but the difference for oxygen is actually -1. So I'm going to write that by the oxygen there, okay, as its kind of formal charge. I'll move on to this middle structure here. I see there's 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So while the difference is 0 for the carbon and the oxygen, for that nitrogen, it's -1. So I indicate the formal charge there. And again, these are not real charges. Like we don't have, this extreme electron density to constitute real charges. We're just really keeping track of electron density. Okay, it's not a complete charge transfer. Transfer of electrons. In this final resonance structure for the nitrogen, I have 1, 2, 3, 4, 5, 6, 7. Wow, I got 7 electrons assigned to the nitrogen there. 4 for the oxygen and 4 for this carbon and 4 for this oxygen. So I'm at a -2, a 0, and this should have been a 5, right? 1, 2, 3, 4, 5. So I'm at a +1 here. And just a quick check, like what we find is the sum of these formal charges is -1 in all 3 cases. And that makes sense per the considerations we discussed earlier, given that this is a polyatomic ion with a charge of -1. So now that we've labeled the formal charges on these 3 different resonance structures, so negative, negative, -2, +1, we want to use these formal charges to actually evaluate which Lewis structure is the best Lewis structure, given that they are not all equivalent. So we have the following guidelines. First things first. For molecules, okay, a Lewis structure in which there are no formal charges is preferable to one in which formal charges are present. Well, this isn't a molecule, this is an ion. So this first one is kind of negated. That being said, if it was a molecule, we don't really like formal charges, okay? We like formal charges of 0, okay? This very often leads to a correct depiction of a molecule, again, as kind of proven experimentally. The second guideline here, Lewis structures with large formal charges are less plausible than those with small formal charges. So we don't really like numbers of, +2, +3, -2, -3. We're looking for, +1, -1, things of that nature. We don't really like charge separation. And with that in mind, it's like when we go back up to resonance structure number 3 here, like this last one, like we have a -2 here, right? So as far as this second guideline, like I'm just gonna keep track of this number 3 isn't really great, right? Because it has that -2 formal charge on the nitrogen. So this last guideline here, it says among Lewis structures with similar distributions of formal charges, the most plausible structure is the one in which the negative formal charges are placed on the most electronegative atoms. So we've already kind of eliminated number 3, right? Like that's the one that has a -2, whereas these previous 2 resonance structures only have formal charges of -1 and -1. So looking at that third guideline, given that we have a similar distribution of formal charges, right, just a single negative and a single negative, we got to figure out which one works, right? And so when I look at this, I see that the formal charge is on an oxygen here. And I know that oxygen is super electronegative, right? One of the most electronegative elements we have, outside of like fluorine. In the second example here, nitrogen is also really electronegative. However, it is less electronegative than oxygen. And between the 2 different resonance structures, we prefer that negative formal charge resides on the more electronegative atom, which is oxygen. So we would deem this, of the 3 possible resonance structures, this is likely to best represent the true nature of this polyatomic ion. Thanks, guys.